And now we'll cover the geometric primitives supported by Hoops Visualize. And when we say geometry in Hoops Visualize, that's referring to graphical primitives that are mostly faceted or vector primitives. In some different types of components, like solid modeling kernels, such as PowerSolid or ASYS, they also use the term geometry, which refers to not necessarily just explicit geometry, but could be implicit geometry, NURB surfaces, and geometry that's represented by what we call BREP, boundary representation. So the actual equations and mathematical definitions of graphical primitives. But in Visualize, with a few exceptions, most geometry is vector or facet based. Okay. So we'll just go through an overview of the different types, quickly cover inserting, editing, give a detailed look on some specific important types of geometric primitives. I'll talk about reference geometry, and then there'll be a few exercises as well. Okay, so in Visualize, we have these concepts of what we call regular geometric primitives. These are things that you insert them into the segment tree and you actually see them. So they actually show up. You actually see polygons or facet sets or arcs, NURB surfaces. And then we also have special primitives, which are cutting sections and lights. So they basically affect the scene, meaning they cut things away or they illuminate the scene. With a few exceptions, you don't see them, you see their results, right? The exception being with cutting sections, we can actually insert the geometry that would represent a plane of a cutting section or the boundary of a cutting section. So that's a little caveat there. A wide variety of our geometric primitives have two parts to them in terms of controlling attributes or how they appear. They have edges and faces. So you can imagine, okay, I have a triangle, I have a polygon, so I can control the outer border. An edge can be drawn with a thickness, a color, and a pattern. And the interior can be drawn. It's called the face. That can have a material property. It could be textured. It could be color. It could be invisible. It could have a pattern on it. Okay. So that's going to be useful for later on. So here's an example of some of the general geometric primitives. Some pictures, fairly straightforward. Some of these have edges and faces. And then it's pretty straightforward to insert geometry. If we look at segment key and the insert routines, there's an insert method for every different type of supported geometric primitive. Cylinders, grids, lines, blah, 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 blah. So we got NURB surfaces, et cetera, et cetera. Okay. And then we have edit routines as well for each one of these. Okay. After a geometric primitive is inserted, you generally would always want to get back the key because that's the only way that a piece of geometry can be referred to. Unlike segments, they can be referred to by keys and names, but this is the only way to refer to geometry. And if you've done a selection on the scene, like a hit test, drew a lasso or a selection box, and then Hoops Visualize gives you back what was selected, it'll give you back an array of keys that you iterate through one at a time. So that's how they're identified. And also if you do a search in the scene graph, again, which is the database, it supports search methods. You also get back keys of geometry. Just a couple examples of the surface primitives, which are the most common. These are usually thought of as the facet sets, and the shell primitive in particular is the most typical one that you would see because it's a very loose type of flexible way of defining faceted information. Okay. These surface primitives are the only ones that support advanced rendering capabilities because they have basically define an array of points and a connectivity of defining the actual faces. So shadows, texturing, multi-texturing, bump mapping, advanced different types of shading capabilities. And they also support different types of edges. So we can have perimeters, silhouettes, et cetera, and we can jump into some of these here. So these can also be degenerate, where they can just be a point cloud. They don't have to have a face list. A face list is created by defining a set of connectivity. And so a shell can just have a points array and no face list, no faces. We'll discuss point clouds or degenerate shells a little bit later. And shells can also have holes. So a face in a shell can have a hole in it. Okay. Polycylinders are another interesting, unique type of primitive. We can see some of the shapes that can be represented via the polycylinder primitive. And it's basically a series of 3D points with radii. So you can imagine that means you can create any kind of interesting spiral or cone or toroid. And we have an interesting polycylinder. Polycylinders also support color interpolation. So at each point in the array, you can define a different color by an index into a color map or a color by actual RGB value, or RGBA value even, I think. And you can get interesting effects like this. So, yeah. Just a little bit more flexible type of cylinder. There are markets and applications that use polycylinders. Anytime like piping systems are being represented, or arrowheads or things, they are used. So a cutting section is made up of one or more cutting planes. And if there's more than one plane in a cutting section, then you get a bounded section. So we look at the first example here, and both views here. We have a cutting section that consists of just one cutting plane. So that's like inserting a cutting plane. Fine, we just cut away everything on the open side of the plane. But if we have two cutting planes that intersect with each other, then we will automatically create a bounded section, as you see there. So we will find the intersection of those and we will bound the cutting plane, right? Otherwise, what you would have seen here is, kind of the last little chunk of this sphere. Separate to the cutting section itself is the intersections of the cutting planes or cutting sections with the geometry, and those faces or edges of intersection can be displayed. In this case, we have a red edge that shows the intersection. That could have been set to a different color. It could not have been drawn. We could have not drawn it at all. And you can gather those and extract them. So what we see here on the far right, on the right slide, is this case where we've gathered all of the faces and probably edges of intersection. We inserted them somewhere else and then just turned off all the other visibility of everything else in the scene, or we unincluded it from our active view, and we're only viewing these extracted faces and edges of intersection. And there's various markets in mechanical CAD that want to have these type of profile views, as you can imagine. So these are very useful. Okay. Reference geometry is very, very similar to include segments. But unlike include segments, when you do a geometry reference, it's only going to refer to geometry from a segment. So remember we had style segment refers to the attributes from the segment. Well, reference geometry is going to just refer to the actual graphical primitives. So we set up geometry will be duplicated. We have a shell key. Okay, we have a segment. We said it was isolated somewhere. We have a shell. We get a reference. In my segment key, we're going to reference that shell key geometry, and we get a key to the reference. And you also notice that the reference itself supports direct application of a modeling matrix, which is kind of nice. So I could have one segment that refers to 1,000 spheres, and each reference itself can have a modeling matrix applied. So I could have all these spheres, organized in some kind of grid fashion, if you will, right? I can create a bunch of, like a Borg cube made up out of all these different subcubes, if I wanted to. So we'll go off and look at this sample called reference geometry. And we'll go ahead and compile and run that and look through it. And we go down to reference geometry and our samples. This is our first time looking at any type of official standalone samples.